Did you know that every year thousands of people walk barefoot across beds of glowing hot coals, some reaching temperatures over 1200 degrees Fahrenheit, and most walk away without a single blister? It sounds impossible, but the science behind it is surprisingly elegant. This isn't about mind over matter or mystical powers. It's about physics, and specifically, two fascinating principles that work together to protect your feet: the Leidenfrost effect and thermal conductivity. Firewalking has been practiced for thousands of years across dozens of cultures. Historical records trace it back to at least 1200 BC in India, and similar traditions appeared in Greece, Japan, Polynesia, and parts of Africa. For centuries, it was viewed as a spiritual act, a demonstration of faith, purity, or divine protection. Priests, shamans, and religious leaders would stride across burning embers as proof of their connection to something beyond the physical world. Spectators watched in awe, convinced they were witnessing a genuine miracle, something that defied all reason and logic. But in the 20th century, scientists started asking a different question, not whether firewalking was real, but how it was possible. What was physically happening between a human foot and a red-hot coal that prevented catastrophic burns? The answer turned out to be rooted in fundamental principles of heat transfer. Heat can transfer between objects in three ways: conduction, convection, and radiation. For our purposes, conduction is the star of the show. Conduction is the direct transfer of thermal energy between two objects in physical contact. When you touch a hot stove, heat flows from the stove into your skin through conduction. The rate at which this happens depends on the temperature difference, the duration of contact, and critically, the thermal conductivity of the materials involved. Thermal conductivity measures how efficiently a material transfers heat. Metals have very high thermal conductivity. That's why a metal spoon in a pot of boiling soup gets scorching hot almost immediately. Wood, on the other hand, has very low thermal conductivity. You can grab a wooden spoon's handle comfortably, even though one end is submerged in boiling liquid. The wood simply doesn't transfer heat well. Now here's where it gets interesting. What are hot coals made of? They're essentially wood burned down to carbon, and carbon, particularly as charcoal, has remarkably low thermal conductivity. So even though a glowing coal might be at 1000 degrees Fahrenheit, it transfers that heat to your foot very slowly. Compare that to a sheet of metal at the same temperature, which would cause devastating, instantaneous burns. The metal would flood your skin with thermal energy so fast that tissue wouldn't stand a chance. The coal, despite being just as hot, delivers its heat at a fraction of the rate. Think of it this way. Imagine two ovens, both set to 400 degrees Fahrenheit. You open the first and briefly reach your hand inside the hot air. It feels uncomfortable, maybe even a little alarming, but you can do it for a second or two without actual injury. Now, imagine touching the metal rack inside that same oven. You'd get burned instantly, painfully, and you'd have a mark to prove it. The air and the rack are at the exact same temperature, but the metal transfers heat thousands of times faster than the air does. That enormous difference in thermal conductivity is the exact same principle at work in firewalking. The coal behaves more like the air in this analogy. It's extremely hot, but it's slow to deliver its energy to your skin. But thermal conductivity alone doesn't tell the whole story. There's another layer of protection at play, one of the most beautiful phenomena in physics. It's called the Leidenfrost effect, first described by German Dr. Johann Gottlieb Leidenfrost in 1751. The Leidenfrost effect occurs when a liquid contacts a surface significantly hotter than its boiling point. Instead of instantly evaporating, something counterintuitive happens. A thin layer of vapor forms between the liquid and the hot surface, acting as an insulating cushion. The liquid floats on a tiny pillow of its own steam, dramatically slowing heat transfer. You've seen this in your kitchen. Heat a skillet until it's extremely hot, then flick water drops onto it. They don't just sizzle and vanish, they dance and skitter across the pan for several seconds, sometimes rolling around like tiny glass beads, hovering on a microscopic layer of steam, completely protected from direct contact with the scorching metal beneath them. That's the Leidenfrost effect in action, and it's genuinely mesmerizing to watch once you understand what's happening. How does this apply to firewalking? Your feet sweat. Even if you don't notice it, the soles of your feet produce moisture, especially when you're nervous. When your moist foot contacts the superheated coal, that moisture can flash into a microscopically thin layer of steam. This vapor barrier creates a brief insulating layer between your foot and the coal. It doesn't last long, maybe a fraction of a second, but combined with short step duration and the coal's low thermal conductivity, it helps prevent burns. Now, the Leidenfrost effect's role in firewalking is debated among physicists. Some argue it plays a protective role, while others believe low thermal conductivity and short contact time are sufficient explanations on their own. The truth is, likely somewhere in between. The Leidenfrost effect may provide an additional margin of safety, but it's probably not the primary reason firewalkers don't get burned. The thermal conductivity of the coals is doing most of the heavy lifting. Contact time is absolutely crucial. A typical firewalk covers about 10 to 15 feet. Most people cross in 4 to 6 quick steps, spending maybe half a second or less with each foot on the coals. That's incredibly short exposure. Heat transfer through conduction depends on duration, so a brief touch limits the total thermal energy entering your foot. This is why instructors tell participants to walk at a steady, brisk pace. Not running, because that pushes feet deeper into hotter embers beneath the surface, but not dawdling either. A confident walk minimizes contact time while keeping the interaction shallow and brief. There is another factor, the structure of the coal bed itself. When wood burns to coals, it becomes porous and fragile. The surface is often covered in a thin layer of ash, which is an even worse conductor of heat than the coal beneath it. This ash layer acts as yet another insulating barrier. Additionally, embers have relatively low thermal mass compared to solid metal or stone. A lightweight coal ember doesn't have as much stored energy as a dense material at the same temperature. When your foot touches it, the coal surface actually cools slightly, transferring limited energy before your foot lifts away. So when you walk across hot coals, multiple factors protect you. The coals have low thermal conductivity, transferring heat slowly. Ash adds extra insulation. Brief contact time limits total heat transfer. Low thermal mass means embers cool on contact, and the Leidenfrost effect may contribute additional vapor insulation. Together, these allow a surface over 1,000 degrees Fahrenheit to be crossed without injury.